Hi everyone, and welcome to our presentation on VGG-based facial emotion recognition. Today we'll be explore how deep learning can be used to recognize human emotion from facial images. We start by highlighting this project matters. Emotion plays an important role in communication and interaction. Our project aims to address the challenge by leveraging a deep learning model to handle various in the image and different facial structures. For our data, we rely on a well-known dataset from Kaggle. It has about 35,000 images, each labeled with one of the seven emotions. The data is already split into training, validation, and test sets. And here, you can see an example of an input image on the left. In this case, happy has a high risk probability, so the model's final prediction is happy. And in this slide, we dive deeper into how many samples of each emotion we have. The distribution can influence how well our model learns. For instance, we have fewer discussed samples relative to happy or angry. So counter
Yeah. So when training our baseline model, we use grayscale normalized to pre-process our data. Additionally, since as Jalen has shown, the dataset is highly imbalanced, we assign different weights on different classes based on the distribution. So the smaller one class is, the higher weights the class will gain. And this will increase the overall performance and the generalization on minor classes. To train the model, we use Atom as optimizer and cosine annealing as scheduler. We also use early stopping strategy to prevent overfitting problem. Yeah, so our baseline model follow classic VGG-16 design, except we delete the last block since it will not increase the performance on our dataset. And here is our architecture of the baseline model. Next, yeah, the total parameter size is 85 megabits when trained using 32 floating precision. Yeah. And our compact model is highly modified based on the baseline model. Specifically, we derive ideas from ResNet and replace VGG block by bottleneck architecture, since mathematically bottleneck use smaller kernel size, parameter size, and deeper architecture while maintaining similar performance. But besides, to mitigate the problem brought by a deeper architecture, we also introduce deep connection and attention mechanism. Yeah, here is our compact model architecture. It achieves a slightly higher performance by nearly 2%, and we reduce its parameter size by nearly 7 times, and therefore increase training speed and efficiency.
Okay, so here we can see the data set. We have about 28,000 training data set and about 7,000 testing data set. And all the images are 48 by 48 grayscale images, which contains seven emotions. And we log value accuracy each epoch and keep the best weights. In here, we can see on this slide. On this slide, we can reveal the result, and we can see our model improves the best checkpoints slightly. However, the parameter drops from 21 megabits to 3 megabits.
So the metrics we use are accuracy, precision, recall, F1 score, and confusion matrix. Here are the performance evaluation results we got for our modules. In the performance matrix by class, the module shows good capability in detecting happy and surprised emotions, but struggles with negative emotions like fearful and sad. This is a common challenge in emotion recognition systems, as negative emotions often share similar facial features. And here is the confusion matrix. We can tell that there are some good ones and bad ones. The main issues are for angry faces, they are often misclassified as fearful and sad. Fearful are frequently misclassified as sad, and neutral and sad faces has a significant confusion between them. The compact model has really similar misclassification performance compared to the baseline module, but a bit more balanced. Last is the ROC curve. The best discriminations for both are happy and surprised for baselines, but happy, surprised, and disgust for compact. Worst are fearful and sad. All classes performs better than random since all AUG are greater than 0.8. So in conclusion, although we only slightly improved accuracy, the number of parameters used in training our compact model are 7 times less than our baseline module. The module optimization achieves significantly efficient gains without sacrificing performance. The new module would be much more practical for real-world deployment, especially in edge computing scenarios or applications where memories and computational resources are limited. And here are our references. Thank you for watching.